Hello students. Today we are going to see one of the important method that is Lagrange's multiplier method. We are going to solve the given LPP in two variables with one equality constraint using Lagrange's multiplier method. So in this method, first of all, we have to define the objective function z as f. Then we will consider the constraint by the variable h. Then we will set up a Lagrangian equation which is L is equal to f minus lambda h. Then we will differentiate this L with respect to x1, x2 and lambda, and we will equate all these partial derivatives with 0. Then we will solve this equation simultaneously and we will get the x1, x2 and lambda, and the point which is known as a stationary point or critical point, that is x naught. It is denoted by x naught. The point of maxima or minima is denoted by x naught. Here x1 and x2 are the coefficients, also known as stationary point. So if there are two variables, then we need to find delta 3, determinant delta 3, whose first row, first column element is always 0. And this first row differentiate h with respect to x1, differentiate h with respect to x2. In this way we can complete the first row, and this is a symmetric matrix. The same elements we will write column wise also. Then here the Hessian matrix part is there. Differentiate L with respect to x1 twice. Here it is x1 x2, then x2 x1 and x2 x2. This part is very simple. While solving actual example, I will explain it once again. Now if the value of delta 3 is positive, then x naught is a maxima. X naught is a maxima. If delta 3 is negative, then x naught is a minima. So this is the condition to decide whether the function is maximum or minimum at the point of at the stationary point. Okay. Now let us see this example. I'm going to solve this example. So here they have given z as z is equal to f, which is 6x1 square plus 5x2 square. Here h is the constraint, which is x1 plus 5x2 minus 7. I'm going to consider L, which is f minus lambda h. So this is 6x1 square plus 5x2 square minus lambda times x1 plus 5x2 minus 7 equal to, this is the equation L. Now to find the stationary points, we have to differentiate this L with respect to x1 and we have to equate it with 0. So this will be 12x1 minus lambda equal to 0. Similarly, differentiate L with respect to x2. So we get here 10x2 minus 5 lambda, and you can equate this with 0. So 10x2 minus 5 lambda equal to 0. And if I differentiate this L with respect to lambda, we will get 0 minus x1 plus 5x2 minus 7, and if you equate this is equal to 0, then multiply by minus sign, we have x1 plus 5x2 minus 7 equal to 0. Now we have this equation number 2. Suppose this is 3 and this is 4. Now you need to solve equation 2, 3 and 4. So if you solve equation 2, 3 and 4 simultaneously, we will get values of x1, x2 and lambda. Okay. So if you want to enter in the calc, you can enter the second equation like this: 12x1, there is no x2, so 0x2 minus lambda equal to 0. Third equation you can enter in the calc: 0x1 plus 10x2 minus 5 lambda equal to 0, and the third equation you can enter in the calc, which is x1 plus 5x2, this minus 0 lambda, and that is equal to 7. So if you enter these three equations in the calc, or if you solve manually also, you will get values like this. Value of x1 is 7 upon 31. 7 upon 31. Value of x2 is 42 upon 31. So your stationary point, which is x1 comma x2, is 7 upon 31 comma 42 upon 31. Now we have to decide whether z is maximum or minimum at this point. Okay, so here as there are only two variables, so we have to find delta 3. Delta 3 is this first row, first column element is always 0. Then if you see your h here, h is, I'm going to write it once again. H is x1 plus 5x2 minus 7. And if I differentiate this h with respect to x1 partially, okay, if I differentiate this with respect to x1 partially, we will get 1. If I differentiate this with respect to x2 partially, we will get 5. So here 1 and here it is 5. The same you need to write column wise. Okay. Now we have L, dou L upon dou x1. You can see here dou L upon dou x1 was 12x1 minus lambda. And if I differentiate this once again, okay, you will get 12. So here this value is 12. Then the next value is 0. Here x2 x1 is 0, and here x2 x2 is 10. You can check this, this is very simple. Now if I find the value of this determinant, okay, if you expand this determinant 0 uh, along the first row, minus 1 into, if you write, this will be 10 minus 0 plus 5 into, this will be 0 minus 60. So this will be minus 10 and minus 300. So this is minus 310. So here delta 3 is negative. Delta 3 is negative. So we know that if the value of delta 3 is negative, then x naught is a minima. So we can find z minimum value. You can put these values in the given function 6 into x1 square. So here 7 upon 31 bracket square plus 5 into x2 square, which is 42 upon 31 bracket square, and if you simplify you will get 294 upon 31. This is z minimum at the point x naught, which is 7 comma 31, 42 comma 31, by using Lagrange's method. So this is here in this example there were two variables and one equality constraint. So in this way the nature of the objective function, whether it is maximum or minimum, it depends upon delta 3. If delta 3 is negative, then x naught is a minima. If delta 3 is positive, then x naught is a maxima. So thank you.